Okay, अस्सलाम वालेकुम। स्टार्ट करते हैं। Last time we were abruptly we closed our connection. Anyway, last time we were at this point. If you can see your slide or screen, uh, so this was yeah. So we just completed from here. So the general solution for this differential equation जो हमने यहाँ पर लिखी है, that is the radial part of the differential equation. It is in fact a linear combination of two functions. One is the spherical Bessel function and the other one is the Neumann function. And the journal solution, which was written here, was for scatter where the potential is much less than the energy of the incoming radiation or incoming particle. That was the starting assumption of partial wave analysis. And so we started with saying that okay, v of r is almost equals to zero or is comparable to zero when we have this condition that v the scattering potential, the scatterer potential, is much less than the energy of the incident particle. So in this sort of assumption, we write the linear combination of the radial function as a linear combination of two functions, that is the spherical Bessel function and the Neumann function. So these are the two functions, and if there were no scatterer, for example, we consider that there is no scatterer, then this BL term, that is the second term, would be zero. And the second term would be zero because BL would be equals to zero. Therefore, in the presence of potential, that is if there is potential, that is if there is a scatterer, then the potential would not be zero, that is v is not equals to zero, and in that case bl, that is the Neumann coefficient, would not be equals to zero. And so in that case this bl would contains the information about this the scatterer, that is the incident particle hits the hits the target particle and is scattered, and this information about this interaction with the target particle or the scatterer is contained within this function BL. Yeah. So in fact, what we are interested in partial wave analysis is to compare these two coefficients, that is AL and BL, such that this would give us the information about the scattering center. That is, we would like to know the ratio of BL upon AL. And so you would see today that we are interested in this in fact ratio, and this ratio would have a very specific name, and this is known as the phase shift, and would correspond to phase shift, and is in fact the quantity which we discussed maybe earlier, and that is in fact the scattering matrix. So we want to know in this in fact the scattering expect analysis, what is the ratio of BL upon, that is the B and upon A, and this would be later on would be called as the scattering matrix. Yeah. And so this would tell us the scattering effect at particular angular momentum. Remember, we have this B and A subscripted by L, small l, and subscripted by small n means that the values of A and B, they are functions of the angular momentum. So there would be, since there are more than one particle, so each would have a different unique orthogonal angular momentum value, and so the scattering effect with the help of this ratio would give us information about scatterer, where the particles are scattered with the where specific particles are scattered having specific values of angular momentum and energy, and that's why we call it as in fact the partial wave analysis, yeah, or partial wave expansion. Yeah. So let's start with, हम यहाँ तक थे, let's start with the free particles, that is let's say we have no potential or scattering potential, and then we would convert into the case where we have potential. And let's say in order to differentiate the two, we would use cosine rather than sine, and the spherical basal function, which we denoted as j sub l as a function of k and r. This is in fact was written as an exponential function. And let's say we consider we start with one of the case where we have this incoming particle, which is free particle and is not, in fact, does not have a scattering center. So let's say we consider the case without scattering. That is, there is no scattering center. Yeah, and we want to know the results obtained when they are compared with the scattering potential. So we would have a contrast between the two results. The one of the result which we will find now, that is the scattering without the scattering center, and the other one would be the one where we study scattering in the presence of the scattering center, and then we compare these two results. So there would be some contrast, and that contrast, in fact, is in the form of the scattering matrix, या जो कि हम आगे चल के अभी निकालेंगे. So let's say for the फ्री पार्टिकल वेव फंक्शन, मैं स्लाइड चेंज कर रहा हूँ. सो हम यहाँ तक थे. इसको कंटिन्यू कर लीजिएगा नेक्स्ट के लिए. सो लेट्स से फॉर द फ्री पार्टिकल, फॉर अ फॉर अ फ्री particle case, that is without the scattering center, the radial wave function r uh, of r is equals to, or in fact this is kr, which is equals to j sub l of kr, which is approximately equals to, हमने वहां पर साइन लिया था, यहाँ पर हम कॉस ले रहे हैं, just to differentiate between the two, because there would be a phase shift. Because in the start we mentioned that there would be a change in the scattered particle, and the particles which would be scattered, they would have a change in phase, yeah, and that change in phase can be represented by different trigonometric functions. So you know, sine and cosine lag or lead by 90 degrees or pi by 2 radians, yeah. So we can use different functions. So we start with cosine, which is kr. So this is not new. हमने इससे पहले भी इस function को लिखा था, which was l plus 1. L plus 1 is the eigenvalues for the angular momentum uh, operator when operated on the wave function. So we know that we have solved this. So we just write the eigenvalues divided by the kr. Yeah. And why divided by kr? Because the result is asymptotic. That is, at large value of r, it would tend to go to 1. That is at, so we can say at kr greater than uh, greater than 1, the value would also be asymptotic. So that is in fact some function. Then we could basically simplify. So this is r, which is equals to j sub l of k r, and then since this is cosine function, so we can write uh, the exponential sort of function, uh, cos of this quantity. Yeah, and so now we can write this cos uh, in the exponential form. So this is 1 upon 2 kr. 2kr का मतलब है 2 comes from the exponential part. So the cos जो function होता है, let's say cos theta, that would be equals to e to the power iota theta minus plus e to the power minus iota theta upon 2. Yeah, and so we can write this cos function with this argument जो यहाँ पर आपके पास argument है. So that could be e to the power iota, and then the argument, which is kr minus l plus 1 pi by 2, this quantity, plus e to the power minus iota kr minus l plus 1 pi by 2 this quantity. And so this is basically the exponential form of this cosine function. And then you can think about this factor, this pi by 2 फैक्टर जो आपको यहाँ पर नज़र आ रहा है दोनों के अंदर, यहाँ पर भी और यहाँ पर भी pi by 2 फैक्टर है. हम इसको सेपरेट कर सकते हैं फ्रॉम this main exponential part. So this 2 pi, sorry, 2k r. So this is 2k r. Then we have e to the power iota k r minus l plus 1 bracket close. And then we have this quantity e to the power minus pi by 2. So we have this iota pi by 2, sorry, iota pi by 2 plus e to the power minus iota k r minus l plus 1 bracket close. So e to the power plus iota pi by 2 the other factor, and this is close. Now you can see this e to the power iota प्लस माइनस आयोटा पाई बाय 2 जो है ये फैक्टर आयो प्लस माइनस आयोटा के बराबर है. प्लस माइनस आयोटा का मतलब है इन अ कॉम्प्लेक्स प्लेन we when we talk about the vertical axis or the y-axis, then that represents the complex axis, and the complex axis in the positive y direction, that is basically plus iota, and then negative y direction, that is minus iota. So we can simply say that e to the power plus minus iota pi by 2 is in fact equals to plus minus iota के बराबर. So this is just plus minus iota. So we can write in place of this factor which is e to the power, in fact iota plus minus iota pi by 2, इसकी जगह हम plus iota and minus iota introduce कर सकते हैं in our radial part. So that equation would then turn to j sub l k r, which is equals to or approximately equals to 2k r, and that factor would be, in fact, this is e to the power iota k r uh, minus uh, so that is, in fact, uh, you could think about so that, okay, so that factor would be e to the power minus l pi by 2, sorry. So that would be iota minus L pi by 2. The we have a minus iota minus, or sorry, plus e to the power minus iota kr minus L pi by 2, or we have a plus iota factor. And then we can just take this factor out. So if we take this factor out, so we have almost 1 upon 2 k r after simplification. So that is minus iota common layer, and this is e to the power iota k r minus l pi by 2 uh, minus e to the, because minus हमने iota common लिया, so that is minus iota uh, k r we have minus l pi by 2 and this factor. Now these two factors, or obviously a minus sign को आप so this is something जिसको आप avoid करेंगे minus sign को, so we can always rationalize, and so 2k r, which is equals to 1 over iota, and then we have e to the power iota kr minus l pi by 2, and minus e to the power minus iota kr minus l pi by 2. So these are two terms. So this is basically some solution uh, which is a solution for linear combination. या यहाँ पर ये वाला पार्ट जो है, पहली टर्म जो है, सो वेयर इज कर्सर, सो ये जो पहली टर्म है, दिस टर्म, दिस इज in fact representing the outgoing spherical wave, outgoing spherical wave, and this factor जो दूसरी टर्म है, that is basically the incoming spherical wave, incoming spherical wave. Yeah, so these are the two waves. एंड अगर आप इसकी प्रोबेबिलिटी डेंसिटी निकालें, यानी दूसरे लफ्ज़ों में हमें अब ये साबित करना है इस केस के अंदर जिसमें हम ये कंसिडर कर रहे हैं कि these two parts, that is the outgoing and the incoming parts, they are in the presence of no scatterer, that is there is no scatterer, then हमें ये साबित करना है कि जो डेंसिटी ऑफ लाइंस हैं, दैट इज डेंसिटी in this particular case when we are doing quantum mechanics, then we would be discussing probability flux. So we want to discuss the probability flux of the incoming radiation and outgoing radiation. If the probability flux of incoming radiation and outgoing radiation वो बराबर होता है, which is a solution for linear combination. So uh, ये linear combination, ये लीनियर कॉम्बिनेशन जो इनिशियली हमने लीनियर कॉम्बिनेशन ऑफ स्फेरिकल बेसल फंक्शन और नॉयमन फंक्शन का हमने स्टार्ट किया था, लिखा था, उसका ये सोल्यूशन है. दिस इज द सोल्यूशन फॉर दैट लीनियर कॉम्बिनेशन. या एंड सो देर इज एन आउटगोइंग स्फेरिकल वेव एंड द इनकमिंग स्फेरिकल वेव. नाउ व्हाट इज important here is to compare these outgoing and incoming spherical waves. So comparison for these outgoing and incoming spherical waves can be done with the help of probability flux. And if the probability flux for the two parts is the same, then it in fact confirms that there is no scatterer. So let's say we consider the probability flux of the two parts. Yeah, and so we want to calculate the probability flux for the outgoing and the incoming. And you know the probability current जो है वो किसके बराबर होता है, J, and quantum mechanically it is equals to J h bar upon 2 iota m. Yeah, the coefficient, and then we have the wave function, complex part of the wave function, derivative of the wave function, minus the derivative of the complex part of the wave function times the wave function. So this is basically the probability flux or probability current density. And इस probability current density या probability flux को अगर हम for solve करें फॉर द केस ऑफ द इनकमिंग एंड आउटगोइंग, जो ऊपर हमने रेडियल फंक्शन रखा है, और इसको सब्स्टिट्यूट कर दें इन दी अबव इक्वेशन, मैं डायरेक्टली रिजल्ट्स लिखूंगा. सो उस सूरत में जो हमारे पास रियल पार्ट का सोल्यूशन आएगा फॉर जे आउट, सो जे आउट मीन्स द आउटपुट पार्ट of the probability flux, that would be h bar upon 2m. So we are talking about the real part and the real part of this quantity. So the real part of minus j star del j del psi. So here we have this iota. If you so आप इसको सॉल्व कीजिएगा. दिस इज अ वेरी सिंपल इनफैक्ट एक्सरसाइज जो हम क्वांटम मैकेनिक्स में किया करते थे व्हेन इन आर 601 कोर्स, दैट इज क्वांटम मैकेनिक्स का 601 कोर्स. एंड सो द आउटगोइंग वेव जो है, जो हमें आउटगोइंग वेव हमें मिल रही, दैट वुड प्रोड्यूस अ करंट डेंसिटी which gives the probability flux or or probability current. इसको probability current density भी कहा जाता है क्वांटम मैकेनिक्स में. इन दिस केस हम उसको फ्लक्स कह रहे हैं. सो दैट इज बेसिकली किसके बराबर होगा, दिस वुड कम आउट टू बी जे आउट, विच इज इक्वल्स टू एच बार के. एच बार के का मतलब क्या है, दिस इज मोमेंटम, एच बार के अपॉन एम r vector, unit vector upon the magnitude of r. So these are the quantities. ये r कहाँ से आ रहा है आपको मालूम है, जो हमने ये ऊपर सोल्यूशन निकाला है लीनियर कॉम्बिनेशन, इसको सब्स्टिट्यूट करेंगे ऑन दी ओरिजिनल वेव फंक्शन साई, और सब्स्टिट्यूट करने के बाद यहाँ पर आपके पास प्रोबेबिलिटी करंट डेंसिटी निकालेंगे. सो दिस कैन बी एन एक्सरसाइज फॉर यू. और इवन अगर आप जो मैंने आपको प्रॉब्लम सेट दिए उसके अंदर भी यू हैव बीन आस्क्ड टू कैलकुलेट करंट डेंसिटी किसी एक क्वेश्चन के अंदर. या ओके. एंड सिमिलरली फॉर फॉर द for the incoming wave उसके लिए भी आप निकालें. एंड सो दैट इज ऑल्सो कम्स आउट टू बी जे इन विच इज equals to minus. The only difference is this minus sign, and this is very important. That is, we have a sign which is minus here. That is, the sign is different for these two. So the only difference between J in and J out is this minus sign. Yeah, and this minus sign then suggests that we have a phase difference between. We would have a phase difference between two particles, then the incoming particle and outgoing particle. So there has to be some sort of a phase change in this sort of process. Yeah. So the incoming, and we could say that the incoming and outgoing fluxes or the probability current densities, they are equal. And when we say they are equal, then iska matlab hai कि no particle is created and no particle is destroyed. Yeah. So that is the incoming and outgoing fluxes are equal uh, since no particle is created nor any particle is destroyed. So this is in fact the conclusion of this part, where we say that in fact there is no change, there is no creation of particle, nor there is any sort of जिसको आप कहेंगे destruction of particle. So and अगर ऐसी बात है, then we draw a conclusion from this. And what is that conclusion? So so in general what we can do that uh, अगर even potentially a scatterer present है, then a scatterer या scatterer present होने का मतलब है कि there is some scattering center, and the incoming particles would see some scattering potential. Therefore, in that case, with the scatterer, the magnitude of in and the out wave parts of this process, they would just be different by a factor which is known as the phase factor, and we call it as a phase shift. Yeah. And so in order to sort of compare our results, or in order to see if in the presence of a scattering potential, we need to look for this phase factor, and we define this phase factor as some phase factor which is basically a multiplicative product with the outgoing wave. So we can conclude here, for the case of no scattering. So conclusion, what is the conclusion here? We say this is this is true. Yani, this is true for a journal case. This is true in journal. In journal, when we say that there is, even in the presence of a scattering potential. Yeah. So this is therefore one would say, therefore uh, even with the scatterer, the the magnitude of n an outgoing wave. Magnitude of, इसको हम इन फ्यूचर अभी हम टाइम इंडिपेंडेंट स्कैटरिंग कर रहे हैं, वी वुड बी डूइंग टाइम डिपेंडेंट स्कैटरिंग एज वेल. सो हम इन फ्यूचर वी would be referring to these two parts of the wave as the in and the outgoing waves. So the wave function would be subscripted by sub psi in and psi out as the two superposition states of the total wave function. Yeah, in and out waves will be will be same, will be same, and this implies that only effect uh, which is which would be apparent will be due to uh, due to some scattering, some phase factor that appearing as phase shift. Yeah. So this would be appearing as uh, phase shift uh, compared to the incoming particle. Phase compared to the free to the free particle wave function. Wave function. Okay, so then we go to the next part. So one would expect for a particle scattered by potential uh, will have some radial part which is modified by this scattering effect. Yeah. So we could say therefore, in the presence of scattering potential, the uh, the uh, the radial part is modified by a factor uh, for the outgoing outgoing part of the radial solution. Outgoing part of the radial solution, i.e. क्या हो जाएगा ये? That is, we would have this radial function r, which was equals to 1 upon 2 k r I. I is the iota. And then we have this factor जिसको हम s से जाहिर कर रहे हैं, s sub l of k. सो एस सब एल ऑफ के का मतलब है कि दिस इज सम फैक्टर जिसको स्कैटरिंग इफेक्ट कहेंगे या स्कैटरिंग मैट्रिक्स कहेंगे. एंड द स्कैटरिंग इफेक्ट्स आर ऑल sort of contained within this factor s sub l of k. So l is the angular momentum and k is the wave vector for the incoming specific wave, and the rest is in fact the same. So this is e to the power iota kr minus L by 2 plus minus e to the power minus iota kr minus l pi by 2 and this factor close. So this is basically the quantity and यहाँ पर हम ये कह सकते हैं this S sub L of K contains the scattering effect, scattering effect, uh, and known as scattering matrix. So इसको हम मैट्रिक्स की सूरत में शक्ल में नजर आएगी आगे चल के. सो फिलहाल लेट्स से वी टॉक वी से दैट इज इट इज इन फैक्ट some factor which contains the scattering effect of the phenomena. So uh, if if indeed if the this scattering potential is present, one need to include the amplitude for having this Neumann part of the in fact wave function, and this Neumann part of the wave function would be almost equals to the spherical basal part which is JL. But then as जैसे मैंने आपसे कहा था ना कि there is a phase shift between the two, and that phase shift between the two is would correspond to or would attribute to using different trigonometric functions. So इधर उधर हमने अगर cost लिया था तो then we can take another function which is in fact the sine, but then there would be a change in the exponential factor by iota, and again if there is a change or difference by a iota factor, then that would attribute to in fact a phase shift, or that would attribute to some factor which is giving you information about the scattering process. So one can say uh, indeed uh, if the scattering is present, or if the scattering scatterer is present, दूसरे लफ्जों में there is scattering, then one needs to the include the amplitude for having NL n sub L of kr, n sub L of kr. NL is the Neumann function in our total wave function, in our wave function. Yeah. So whose asymptotic फॉर्म को हम कैसे लिख सकते हैं, वो उसी तरह से एक्सपोनेंशियल फॉर्म की सूरत में. सो this r would be almost equals to approximately equals to n sub L of kr, which is in fact approximately equals to sine of function which is kr minus L plus 1 of pi by times pi by 2 whole. So what makes it asymptotic is divided by kr. So it is asymptotic because then it is divided by kr. So at larger distance the amplitude goes down. So we have r which is approximately equals to n sub L of kr, which is in fact. So ये उसी तरह से solve करेंगे. You would see that there would be a factor of minus iota in the upstairs, and this factor of minus iota in the upstairs would be cancelled by an iota in the downstairs, that is a numerator or denominator, and so this is minus iota upon 2 kr iota. So this would be cancelled. सो ये आप कर सकते हैं अगर आप इसको एक्सपोनेंशियल नोटेशन में उसी तरह से जो हमने पहले किया था, के आर माइनस एल पाई/2 और फैक्टर प्लस ई टू द पावर माइनस आयोटा। सो रिमेंबर साइन जो है कॉस में ई, दो जो एक्सपोनेंशियल फंक्शंस हैं माइनस एंड प्लस के साथ, उनके दरमियान में साइन माइनस आता है एंड इधर सॉरी प्लस आता है, और साइन के केस में माइनस आता है। एंड सो व्हेन वी यूज दैट फैक्टर ई टू द पावर प्लस माइनस आयोटा पाई/2, तो वो आपके पास ऑटोमेटिकली प्लस हो जाएगा। सो इट इज सॉर्ट ऑफ conjugate. Uh, oops. So this is times kr. So which is kr minus l pi/2. Yeah. So this is in fact the equation जो हमारे पास आ रही है फॉर दी अदर केस। ओके, सो इसका मकसद ये हो गया। सो वन वुड से दैट अगेन इट इज़ अ लीनियर कॉम्बिनेशन जो हमने शुरू में लिखा था, एंड दैट इज़ अ लीनियर कॉम्बिनेशन कंटेनिंग ए जे सब एल ऑफ के आर प्लस बी एन एल सब एन एल एन सब एल ऑफ के ऑफ आर एंड इन सम एसिम्प्टोटिक रीजन। और अगर हम ये सब्स्टिट्यूट कर दें इसके अंदर, then we would have the total wave function जो कि you have to substitute the value of JL and you have to substitute the value of NL, yeah, and when you substitute